It's in the pack, so you can read up. Basically, we're looking at something called the activation energy. So we plot the log of resistance against time temperature. And the relationship between them gives us an idea of the activity, the activation energy. This is not the activation energy during hydration. It's the activation energy in connection to the resistance. So we can pick that up as EA over RG. RG is the universal gas constant, therefore it's a constant, which means the apparent activation energy is a value. We did this work for that structure, then I looked at all the work done by John McCarter for a lot of other structures. It's all within the range of 3,600 to 4,500, depending on the different concrete. So it's a very consistent concrete related property. Okay. And you can use that function to compensate for temperatures, for resistivity. So that's resistivity, and that's the resistivity independent of time, and you can use that function and back into that. So which means, back here. So resistivity at any temperature x is equal to resistivity at a temperature y multiplied by a temperature function. You can program that into Excel, that's what we did. Okay, everything is in Kelvin. So this is pre-compensation as to post-compensation. Now, are we doing good? Very much so, we're doing very good. But see this tiny hiccups here? I'll explain that. But essentially we're above 1, and the 70 mil seems to be lagging its feet compared to the 40 and the 20 mil. Why would that be? The top of the concrete has a waterproofing layer, has another concrete layer, waterproofing layer, bitumen layer. Okay. Assume there's no new water coming from the top. If you had new water coming from the top, this 20 millimeter would have been at the bottom. Yes? Okay, so that's case 1. Case 2, there was already water in the concrete, right? When we sealed it up. So the water has to escape. It can't escape above it. It's against the laws of gravity. Also there is payload on the top. So it will escape downwards towards what's called the breathable membrane below. That's why we were trying to avoid the breathable membrane. It seems the moisture is moving towards the breathable membrane, and the fact that resistivity is increasing, we're reasonably confident that it is breathing. Because if it wasn't breathing, we would have seen that to be a bit more stagnant behavior, but more towards it would have been flattening towards 1. But it's not, it's improving. Okay? And it's a very much of a gradient. And we also plotted the rain data to see would the rain data shift it. Okay? And these are the peaks of the rain data, and it doesn't seem to have any influence on resistance. That gives you confidence. That means it's not connected to rain, which means it's sealed from the environment. Okay. Okay. Anything else? Yeah, here, if you look closer to the start, this is 3 months after the concrete was installed, and then suddenly the resistance drop, and then a bit later it picks up. Okay, so there's something here happening, and thankfully we took a picture. When we went in the structure, we always take pictures and we capture the information. At that time, we have seen a moisture patch here below the deck. What was happening was the rubber joint has failed at the top. The contractor was liable for up to a year to fix it. So they saw the patch, they came back and they fixed it towards later January. When they fixed it, it started picking up again. So it could have started, resistance could have started somewhere here, and then because of the patch it started going down, and because they fixed the patch it started going up again. In no means that to say the patch won't appear somewhere else. The patch did appear somewhere else a bit later. So, but at least that means the sensors are very sensitive to pick these things up. Okay. So we started with a few questions at the beginning. Okay, the first question was the rubber joint staying intact and not letting water? Answer is yes. When it failed, we knew, and they fixed it, and it worked. Does it work long term? The amount of visits they had to do afterwards doesn't suggest that it'll work long term. But we're aware, and they're aware, that the current technology is not sufficient for us to use it in expansion joints. That rubber sealant only works up to certain years, and after that it'll fail. Rubber will also become very rigid and will break. Okay, so shrinkage, do we see any shrinkage issues? Nothing noticeable at this stage. If we had shrinkage, the sensor was installed very close to the old concrete, that would have detached. We didn't see any detachment. And the 20 mil where things would have happened seems to be doing well. Is moisture allowed to escape? When we closely analyze the data, we see the moisture seems to be going downwards. I'm not yet sure if that downwards includes dissipating into the air, but I know it's going downwards. And the 70 seems to be increasing in resistance. So it's not just collecting water. That's all I can say at the moment. Okay. There is limited movement of moisture and ions from parent area to repair area. The very fact that the resistance is increasing, that means we're not getting any movement from the parent concrete to the new concrete. If it was, resistance would not have increased. Now, bear in mind I don't have the first 3 months of data, so things would have moved in initially. I'm only taking a ratio, so things would have moved in, resettled happily there, and then thereafter it's increasing. But it doesn't matter because resistance is increasing, which means it's unlikely to corrode. So ultimately that sensor gives you a bit of confidence that your repair is working. They have distributed this information to their chain of database and chain of people doing repair as best practice, with the knowledge that they need to be telling companies to find something new. And that's how it works in the UK. We just tell them, look, we know it's not working, can you come up with something else? And they might actually come up with something else. They probably already know what to do next. Okay, so it gives you an idea how sensors can be used to do performance assessment. Any questions? Don't have to ask questions. Yes, yes, and I think it's in that picture. It was developed by John MacArthur, so I think it's patented to Hereward University. But they sell it through Amphora, I think. That one. So a lot of research went in to make this a very stable system. So you're essentially buying that technology as well. You can make the sensors yourself. We had chatted of how to make the sensors, not really complex. But if you want to buy the assembly, I think it's patented, so you'll need to pay for the assembly. Sensors, I think each of them could be anything between 200 to 300 pounds per sensor. What does that come out to be? 20 to 25,000 rupees per sensor. But it has the capability to do corrosion, it has the capability to do moisture, ionic transport, has the capability to do temperature. So some people might prefer all of these capabilities. And I think there's the new technology is there's a wireless module behind it, so it's not wired anymore. You can tie this end to the rebar, and that's how it works. Sorry? Up to your desire. So we collected data for every 10 minutes in the first 6 months. I regretted that decision because we had 72 lines of information coming in every 10 minutes for 6 months. In the instrumentation box we put in, we can put up to 72 channels, 72 lines. Here, depending on the level of information you want. So this is one channel, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 in here. You don't need to have 10. You can just disconnect some of them if you don't need all of that information. So 10 channels are there. You can go up to 76 with. So the data logger was, for in our case, we work with a company called Instrument Solutions because they're a research-based unit, so we prefer that. They had a single module which can go 4 of these sensors, okay, and then they have a multiplexer. So, but they can have 9 of the multiplexers. So even with 2 of those, so the main and the multiplexer, we had 76 lines. They can have 8 more capability. So you can go as much as you want, but you need a reliable electrical wiring person to tidy this up. Our monitoring box looks like a chicken mesh. It's just wires after wires everywhere. Okay. Because you're in the long-term game, you can smoothen the data. So you can see the signal loss here. Okay. That signal loss, we still don't know why the signal loss happened. But any other signal loss we had, we knew what happened because we're meant to go and collect the data. Quite often that's not possible for us to go and collect the data. So because it was so frequent measurement every 2 hours, in this case, we lost data because we didn't go back to collect it and it overrun the capability of it. So for a structure like that, after the initial 28, 56 day phase, I suggest maybe a 6 hourly data is more than enough. So 1 data every 6 hours because you're going to pick up the morning and the evening and the night and the afternoon. So we did pick up a lot more data at the beginning and that's why we lost the memory. And also we weren't very efficient in using it because we had temperature sensors installed in the concrete, part of the structural study. And that was all coming into the channel, so we were losing a lot more channel space for it. So if we were efficient, 6 months would have been perfectly fine. Visit every 6 months. The data logger that we used has something called a mobile port. So you can put a mobile mast and it will send the signal back. So we have the same data logger system in 2 places. One is in Edinburgh. We know the Scottish bridge that I showed you a few days ago. There are sensors in it and that has a mobile mast and a solar panel. So it sends the signal back to Heidelberg University. They don't have to go. They don't probably go for years. There's another one in China in the Hangzhou Bay Bridge. That also has a mobile mast. And those 2 are solar powered. It's a tiny panel. This one is battery powered. The way it worked out is we had a battery and we have a backup battery charger from the electric lamppost. So the electric light, not floodlights, what's it called? Traffic light, the normal light on the bridges. So we connected a line to that so it can charge the battery. Without that, the battery will last as long as the battery lasts, normally 4 to 6 months, no problem. But if you're not going every 6 months, you need some form of recharge capability. So. Into the reinforcement cable type. Yeah. You can use glue if you're putting it on the mold itself, but cable tie to the reinforcement steel is better. Plastic cable tie, not metal. Yeah, that's fine. That's fine. Okay. Wood actually, glue especially would because glue might yield. So if you have a glue yielding, then you're going to get a bit of strain from the glue. But you should always have a perfect spot somewhere on a metal plate with the glue and the same installation techniques, so that you can always compare against it. Yeah. You should, yeah. That's all part of the construction sequence and construction technique. So my suggestion would be to test it out and see what strain. If you put it on a strong metal plate, okay, change the temperature and then see if it moves if it gives you a strain value. If it does give you a strain value, that's your compensation coming in. Okay, and if you put it on an area where I presume the supplier is doing that kind of compensation study.
Magnetic mounting plates are given along with the sensors.
They would have done that study. I don't think they would give.
But they're not given any kind of elevation factor. So whatever the first readings we get, we take it as a reference. So we don't take any kind of correlation with
So you're using the resistance ratio kind of approach then. Yeah. Okay. That works because you're only looking at change in that sense, not an absolute value.
other kind of sensors where band sensors are being used. So we directly get the reading.
Okay.